Today is Friday, and to paraphrase Rebecca Black, it's Friday, Friday, everyone get it. I don't know the song, but it's Friday, and we're working on section 5.2 in our chapter on polynomials, and 5.2 is simply called gathering like terms. So we already know what a term is, and to refresh your memory, a term is an expression. Terms are an expression made up of numbers, variables, and or both. So examples we said. For example, we'll just do it again. -2 is an example of a term. XY is an example of a term. Or 3x squared y4 is an example of a term made up of course, this would be made up of a variable multiplied by a variable. This would be made up of a number multiplied by a variable 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 multiplied by a variable. You get the idea. When we talk about gathering like terms, the definition of a like term is terms that are identical, terms that are identical, except, Mr. Hankinson, except for their what? Anyone want to take a guess? What do you think? Not the variables, because that would mean that they're not like terms. They have the exact same variables and the exact same combination of variables. The only thing they don't necessarily have to share is their coefficient. So, for example, 2x and -3x are like terms, right? Because they have the exact same variable, but they have different coefficients. So if I drew them, I would draw an x, and I would draw an x. And what I'm using here to draw those is those long, slender algebra tiles that we call x's. And to draw these ones, I would draw the same long, slender algebra tiles, but I wouldn't shade them in. But they're the exact same shaped tile. So that's what you kind of have to think about. What would it look like? All right. If I look at, let's say I look at -3x squared and 2x squared. Those would be identical terms because the term themselves, they are x squared tiles that I would use to draw, and the only thing they differ by is their coefficient. So I draw them with three open ones. That's -3x squared. That's 2x squared. And those would be like terms. Now, examples of things that are not like terms, what you think they might be, is let's say 2x and 3x squared. They are not like terms, not like terms. Because yes, the coefficients are different. The coefficient here is 2 and the coefficient here is 3. They can be different. That's okay if the coefficients are different, but we don't have the rest of the term being like. And we can see that best illustrated if I was to draw two x's, I would draw these, and I would draw x squared tiles like this. So the algebra tiles actually help us visualize the fact that they aren't like terms. Right? So that's kind of important. So not like terms. And you can triple underline the not. Does that make sense to people? So basically, when we're talking about gathering like terms, in a second here, we're going to be dealing with identifying those terms within a polynomial that are like terms and being able to think about what we're going to call algebraic zero pairs. And we'll see that in just a second. So then if we go back to our show you know questions, it says give an example of three like terms. So again, the ones I gave you were, let's say, 2x and -x. Those would be like terms. Because the only thing differing here, the coefficient of 2, the coefficient, what's the coefficient of -x, Hankinson? No, it's not. It's -1. Right? But yeah, the coefficients are different, but the rest of the term itself shares all of the same parts. Same variables, same exponents on those variables, etc., etc. Another one would be 3xy and xy, right? Those would be like terms because they contain the same variables with the same exponents on those variables. And finally, we do -2x squared y and 4x squared y would be like terms. Everything's identical except for the coefficient. Now, just as a aside, just a note. Let's go with x squared y and xy squared. Are those like terms? The answer is no. They're not like terms. Are not like terms. Even though they have the same variables, and they have what appears to be the same exponents, those exponents are on different parts. This, if we think about it, is x times y, and this would be x times y, which is different, right? Because if x equals 2 and y equals 3, this would be 2 times 3, and this would be 2 times 3, which are not going to give us the same answer. Okay? Are we okay with that part? Does that make sense? Yeah. Okay, good. And then the last question, B, says identify the like terms in the following groups. So we have 6t, 3s, 6t squared, 6st, and negative 8s. So what I'm really looking for is I'm ignoring the coefficients. I'm just looking for the parts of the expression. Are there any other of those 5 that have just a variable t, Hankinson? Is there anything there that just has a variable of t? So if we look at this, what we have to identify, let's ignore the coefficients. This is a t, this is an s, this is a t squared, this is an st, and this is an s. Do you agree with that? If I ignore the coefficients, those are the terms. So are there any other t's there? No. So this 6t does not have any other like terms in that range. Is there any other s's? There's one here, and there's also one here. So what we would say is 3s and negative 8s are like terms. Period. And that's done, and that's done. Is there any other t squares? No. Is there any st's? No. So the only like terms in that entire list were 3s and negative 8s. If we look at our second show you know, it says combine like terms. Now there are 2 methods that we can combine like terms. 2 methods. Ultimately, you're only going to use one method, but we're going to practice both methods, and then ultimately you're just going to use the second method from this forward. The first way you can do it is to draw it, right? So what I'm going to do here is I'm going to draw this polynomial of 4 terms. I'm going to put a 5x, a 1x, 2x's, 3x's, 4x's. That's 5x. So right there would be the term 5x. Then we're going to put a negative 3x squared. There's negative 1 3x squared, negative 2 3x squared, negative 3x squared. Then we're going to do a positive 2x. There's 1x and 2x. And then we're going to put a negative x squared. Okay. So what we're going to do now is we're going to look at our picture, and we're going to ask ourselves, I'm going to put 2x here. And this is going to be a negative x squared. Let's go back to Jacob. Jacob, do you see any shapes that I drew that are the same in those 4 terms? Any same shapes? Yes. We have x's over here, and we have x's over here. So when we combine those 2 like terms, what do you think we're going to get if we combine those 2 algebraic shapes together? What is it going to become? It's going to become 7x, right? So this plus this is going to combine to make a new term of 7x. Okay? And then these 3 here and these 3 here are going to change to become negative 4x squared. So essentially, all we are doing here is identifying the like terms, right? All we are doing is identify like terms and combine the, Sophie Kong will tell you, coefficients. So all we did there was identify the like terms and just combine the coefficients, right? Does that make sense? Now, if we did that without drawing the picture, we could still do it, and this is method 2. So method 2, this is draw. This is method 1, which is draw it. Method 2 is examine and combine. Examine and combine. Examine and combine. Coefficients and combine. I'll put examine and comb. That seems reasonable. So going back to that question, I had 5x minus 3x squared plus 2x minus x squared. So here's what I like to do. If you're new to this, what I would advise you to do is just kind of box it up and separate the terms with the operation signs like this. Okay? And instead of drawing it, you're just going to look and combine. So I'm going to start with my x's. I have 5 of them here. I have 2 of them there. I'm thinking I'm going to combine those exponents, or the coefficients, excuse me. So I get 7x. I get a negative 3, and I have to know that that's a negative 1, which means that's going to combine the big negative 4x squared. Piece of cake, not hard at all. Right? So if you think about what happened here, I started with a 4-term polynomial, but I was able to reorganize it into a binomial by gathering like terms. They still are the same thing, they're still the same value, but I'm able to gather the like terms and combine them like that. Now there is one thing that I should note. Note, when gathering like terms, you should start with highest degree terms first. So, what did I gather first? I gathered my x's first, didn't I? And then I gathered my x squareds second. But I should have gathered my x squareds first and my x squared second. So what should this actually be if I did that? What would that change into if I gathered my x squareds first and then my x's? That's right. Negative 4x squared should have been my first term, and then plus 7x is my second term, or positive 7x is my second term. Back after. Let's look at B. So using those two methods, if I drew it, I'd have 1x, 2x, negative 6. I'm going to switch over to integer chips for a second. Negative 6. Negative 2x is going to be open ones of these, and a positive 1 looks like this. Now this is going to be different than the first one, because what happens when we combine the x tiles? When we think about this, these two and these two are going to make like an algebraic zero pair, right? Remember in grade 7 when you learned about adding integers and use the chips? Well, that's the exact same thing that happens except with algebra. 2 negative x's and 2 positive x's, because remember, the negative x's are really the opposite of x. When you combine two numbers that are opposites, you'll always end up with 0. And this negative here and this positive here are going to cancel each other out. So the simplification of this is going to be simply the number and the monomial negative 5, right? That whole polynomial of 4 terms, when I gather the like terms, is going to be simplified down to just a monomial, just the number negative 5. That's the modeling aspect. If I box it up and think about those 4 terms, cut them off between their signs, start with my highest degree terms. A 2x and a negative 2x make 0. A negative 6 and a positive 1 make a negative 5, and that's my answer. Okay? And the last question, C. A k is the same thing as an x. We'll just keep it like that. Negative 2x or k squared looks like that. Positive 3 is going to be 3 integer chips. Positive 5x squared negative 3k or negative 3x. Remember, the variable doesn't matter in terms of these shapes. K's, x's, m's are all the same little rectangle shape. And negative 4. Okay. So now what we're going to do is we're going to combine. Which one should I start with pictorially? Which tile should I start with? The k's or the k squareds or the 3's or what? Gavin, which one should I start with? The highest degree term first, right? You have it in your notes there, remember? It says, note, when gathering like terms, you should start with the highest degree terms. So if we look at that array, which ones are the highest degree? The k squareds, right? So these two and these two are going to make what? 0. And what I'm going to be left with is just these three right here, which is going to be 3k squared. So now they're all done. I got those taken care of. One of these and one of these is going to make a 0 pair. What am I left with? Negative 2k. Now those are gone. We got those. These three here and those three there are going to cancel each other out. What am I going to be left with? Negative 1. And that is the solution. This used to be a 1, 2, 3, 4, 5, 6 term polynomial, Andrew, but by gathering like terms, I ended up with just a trinomial. Okay. And again, without modeling it, method 2 would be box it up, keep your things together here like this, identify your highest degree term, those are your k squareds, negative 2k and positive 5k, combine those coefficients, you end up with 3k squared. A positive k and a negative 3k make a negative 2k, and a positive 3 and a negative 4 still make a negative 1.